Video 2. We're going to define the complete bipartite graph, the complete multipartite graph, the connectivity number of these graphs, and we're going to define the complement of a graph. So first, the complete bipartite graph. A graph is a complete bipartite graph if there exists a partition of the nodes into two parts. Let's call them part A and part B, such that any pair of nodes where one node is in A and one node is in B, then those two nodes are connected by a link. On the other hand, any pair of nodes in the same partite set are not connected. For example, we have two partite sets below. This network has 5 nodes, 2 in one partite set, 3 in the other. We see the 2 nodes are not connected. We see the 3 are not connected, but every edge that can exist between the two partite sets exists. We denote these graphs by a K sub M comma N. In this case, K sub 2 comma 3, indicating that there are 2 nodes in one set and 3 in the other. And we use the capital K because every edge that can be between the two partite sets is in. Notice that this means that the graph has M plus N nodes all total. And this shows us that what we've been calling the star graph is actually an example of a complete bipartite, where one of the partite set has 1 node and the other partite set has M nodes. This can be generalized. We wouldn't have to necessarily partition our node set into 2 partite sets. We could partition them into, say, K partite sets. And so we would call this the complete K-partite graph, where there are K sets of nodes. So the complete multipartite graph is a graph where there is a partition of the node set into K parts, such that any pair of nodes that are in the same partition, or the same part of the partition, are not joined. And any pair of nodes where one is in one partite set and one is in a different partite set, then they are joined. And so the complete bipartite graph is a complete multipartite graph where there are just 2 partition sets in the partition. So we'll denote the complete multipartite graph with K partite sets by K sub, and then the size of each of the partite sets, M1, M2, and since there are K of them, up to MK. We're interested now in the connectivity number of these complete multipartite graphs. We know what the connectivity number of the K1M is. It's 1 if we remove that one central vertex. So what do you think is the connectivity number of the KNM? It might depend on which is bigger, the N or the M, because the connectivity number, recall, is the minimum number of nodes that you can use to increase the number of components when you remove those nodes. What about the M1, M2, up to Mk. As I mentioned before, it might depend upon the size of the partite sets. So without loss of generality, we can order the size of the partite sets, choosing M1 to be less than or equal to M2, and so forth up to Mk. Then the connectivity number would have to be M1 plus M2 all up to Mk minus 1, leaving just the nodes in the last partite set. So we would have to remove a lot of nodes to disconnect the graph, a lot relative to how many there exist, and therefore these graphs are highly connected. Now let's talk about the complement for a minute. What is the complement of a set? The complement of a set requires that we identify a universal set. And then the complement of a set A is the set of all elements in the universal set that are not in A. For example, if our universal set is the set of all integers, and the set A is the set of all even integers, then the complement is the set of all odd integers. Or if our universal set is the set of all real numbers, and A is the set of all positive real numbers, then the complement, of course, is the set of all negative real numbers, together with 0. So what is the complement of a graph? The complement of a graph would first require us to consider what is the universal set. So the complement of a graph we measure against the universal set being the set of all possible edges. Then the complement of the graph has the same node set as the original graph, but its edge set is the set of all edges that are not in the original graph. For example, this was our first graph. It's a complete bipartite. Now, what would be the complement of this graph? Since there are no edges in either partite set, every edge would be in the complement. And since every edge runs between, then in the complement, no edge would run between. So do you agree that the complement of this complete bipartite graph would be a K2 and a K3, and they would be disjoint? So we would denote this as the disjoint union of a K2 with a K3. What is the complement of the complete multipartite graph with K-partite set? Each of the partite sets, recall, has no edges. So the graph induced by each of the individual sets in the partition would now be complete. And again, since in the original complete multipartite graph, all edges between the partite sets were there, no edges would be connecting these complete graphs of size M1, M2, and so forth. So we would wind up with the disjoint union of K complete graphs, each one the size of the original partite sets. In the special case, suppose all the partite sets have the same size. So suppose we're looking at a case of P, B, B, B. Say that there are M of them. what would we have for the complement of that? Each of the partite sets of size Kp would now be a complete graph on P vertices. And since we said there are m of them, we would have m disjoint copies of a Kp. So we've talked about the clustering coefficient and the connectivity number of a network, and we've looked at some special families of graphs to study these concepts. So what we're going to do in our third module is compare the connectivity number with the clustering coefficient using these special families of graphs. So what we have done is we've defined the complete bipartite graph. We saw that that was a special case of the complete multipartite graph. We talked about the connectivity number of these graphs. And we defined the complement of a graph.